Hello, welcome to the lecture 7 of the course Transportation Network Analysis. So, in the last class, we had seen the motivation for developing new solution approaches for solving integer programs, because it is not possible to use the solution approaches that we had seen for the linear programs and then we use them for solving the integer programs. So, this branch and bound algorithms is a general strategy for solving integer programs. We will be referring to integer programs as IPs in the short in this course. This strategy, branch and bound, is also applicable to solve general nonlinear optimization problems, that is other category of optimization problems, but we will be only keeping our focus to solving the integer programs. So, this branch and bound is a systematic enumeration technique of candidate solutions by means of state space search. So, what does it mean here? First of all, what is enumeration here? Enumeration is listing down all the feasible solutions and then we go through all of them and find the optimal solution. So, that approach can be taken for any optimization problem that has a finite set of solutions. So, any combinatorial optimization problem can be solved using that. But it is a very naive approach, because it will happen that when the problem size becomes very large, for example, when you are solving the traveling salesman problem and you have millions of nodes, so then listing down all the possible solutions and then finding the best one may not be very feasible. Okay. Whereas this branch and bound is a much smarter or systematic technique as compared to pure enumeration technique. So, what it will do is that it will divide the whole feasible region into some solutions, and it will tell that some set of feasible regions we do not need to look at, because there is a way to argue that we will not be able to get optimal solution in that region, and therefore we need to just keep a focus on another set of feasible solutions, and in that way we will be able to focus on a smaller set of feasible solutions as compared to looking at all the feasible solutions. So, in branch and bound, the set of candidate solutions is thought of as forming a rooted tree with the full set at the root. So, what does it mean? That at the top level of this branch and bound, we have the set of all of the candidate solutions or the feasible solutions, and then as we will go down this tree, we will be dividing this set of feasible regions into different partitions, or we will also refer to them as different branches. So, these different branches of the tree will represent subsets of the feasible solution set that we have. Okay. So, we will be dividing this whole feasible region into various different subsets or branches you can think of, and then we will be saying that maybe some branches there is point of focusing on and some branches can be discarded, because there is no reason that we will be able to find optimal solution there and so on. So, before enumerating the candidate solutions of a branch, the branch is checked against the upper and the lower estimated bounds on the optimal solution. Okay. So, what does it mean? So, before we start to focus on all the solutions of a particular region of a feasible set, that is a particular branch, we will be able to sometimes argue that what is the best solution this feasible region can give, and somehow if we are able to argue that we already have a solution which is better than what the best solution this branch or this feasible region can give, then there is no point in looking further into that branch or region. So, we can then discard that branch or region. Okay. So, this will become clearer with an example that I will be discussing in the next slides. So, this statement is saying a branch is discarded if it cannot produce a better solution than the best one found so far by the algorithm. Okay. So, for some technique we will be able to sometimes say that a particular branch will not be able to give a solution that is having, say, objective function value say equal to some value x, and suppose if we are maximizing this optimization problem and we already know a solution y which is integer solution and that is greater than x. So, then there is no point of looking at this feasible region or this branch that gives the best solution as x. So, this is a simple example to illustrate what I just said here. So, if a branch A achieves an objective function value of 100, okay, and suppose we are maximizing and the branch B's objective function value is at most 80. So, there are two branches here, one gives an objective function value of 100, that is the best solution it can give is 100, the other branch is giving the objective function value of at most 80. So, somehow we know that it will not give you anything more than 80. So, then we can prune the branch B without breaking it into further branches. So, what it means is that pruning a branch means that we will not look further in that branch. So, we will not closely evaluate the solutions that are present in that branch, because we already know that even if we look at all of the solutions in this branch B, it will not give any solution that is having objective function value greater than 80. So, why to spend our time there when we already have a solution that gives the objective function value of 100. Okay. So, pruning means cutting down. Okay. So, in order to understand how this branch and bound algorithm works, we will be looking at an example here. So, this is the objective function maximize z equal to 4x plus 5y, where we have these constraints x plus 4y less than or equal to 10, 3x minus 4y less than or equal to 6, and x and y are non-negative integers. On the right side, we have this diagram where the black points are representing the feasible solutions of this integer program. This orange space actually is the feasible region for the corresponding linear program. Okay. So, suppose instead of this optimization problem, if we relax x and y to take continuous values, that is, instead of this constraint, if we had x greater than equal to 0 and y greater than equal to 0, so then the feasible region will be this orange portion here that is shown. Okay. And these black points otherwise are the feasible region for the integer program if we restrict both x and y to take only non-negative integer values. Okay. So, the first step in solving the integer program in this branch and bound algorithm is that we solve the corresponding linear relaxation of this problem. Okay. What does this mean? Linear relaxation means that we do not restrict x and y to be just integers, and instead of x and y being non-negative integers, we are putting now this constraint x greater than equal to 0, y greater than equal to 0. Everything else stays the same here. So, since this is a very small linear program, that is, the number of extreme points or the corner points in this linear program will not be that many. So, we can look at all the corner points or the extreme points here and then find the optimal solution. So, the optimal solution for this linear program will occur at the point 4 comma 3 by 2, and the objective function at this point will be 23.5 here. So, when you put x equal to 4 here in this objective function and y equal to 1.5 here, so you will get this 23.5 here. Okay. So, remember that this is not the optimal solution for the integer program that we originally started with. This is the optimal solution for the linear program. Okay. Now, one more thing to notice here is that the optimal value of the original integer program that we targeted to solve, that cannot exceed the optimal value of this linear program. That is, the optimal value of the integer program cannot exceed 23.5 here, and the reason for that is the feasible region for this integer program is a subset of the feasible region of this linear program that is being shown here. Okay. So, therefore, whatever optimal value that we get for the integer program, that can either stay the same as the corresponding linear relaxation of the linear program, or it can be lesser than that. Okay. So, this 23.5 is an upper bound on the objective function value of the integer program. Okay. Now, since we got this solution 4 comma 3 by 2 as the optimal solution for the linear relaxation, now here this y equal to 3 by 2, that is y equal to 1.5, is not an integer. Okay. So, we will be considering two cases here. One is y less than or equal to 1 and other is y greater than or equal to 2. So, let us look at the new linear programs that we get. So, remember that the original linear programming relaxation of the integer program was this much, was having this much feasible region. Okay. And now what we have done is that we have divided that feasible region into two smaller regions. The first feasible region is obtained when you put whatever constraints you had in the original linear program plus this constraint y less than or equal to 1. With that, you will be getting this feasible region here, the one shown by orange here. And when you put this constraint y greater than or equal to 2 in addition to the constraints that were already present in that linear relaxation, then you will be getting this blue or the purple region here. Okay. And you can see that since we are interested to solve the original integer program, there is no feasible region in this white portion here, because the feasible points of the integer program are restricted to be integers. So, this is y equal to 1, this is y equal to 2. So, there cannot be anything which is lying here. Okay. So, that is why there is no point in looking here. So, that is why now we have decided to focus on these two regions here. One is y less than or equal to 1 here, and the other is y greater than or equal to 2 here. Okay. Okay. So, let us first solve the original linear program with the additional constraint that y is greater than or equal to 2. When we will do that, then the optimal solution will be at the point x comma y equal to 2 comma 2, okay, and the objective function we will be getting will be z equal to 18. So, again this optimal solution can be obtained by looking at the corners of the feasible region of this linear program here, because it is a small linear program. So, the number of extreme points or the corner points are not that many. Similarly, we can solve the linear programming relaxation with the original constraint that we had plus the constraint y less than or equal to 1. Okay. So, when we do that, then we get this optimal solution here, that is 3.33 comma 1 with z equal to 18.3. These are approximate values here. So, this actually is 3.333, it goes like this, and similarly this z value goes as 18.33, but approximately we have written it like this here. So, just one point to again remind you is that when we were solving this first linear program, so there we had the constraints for the original linear program that we had plus y greater than or equal to 2. Okay. So, those constraints we have not thrown away, we still have those constraints, just that we are adding one more constraint y greater than or equal to 2, and then the feasible region here is the purple or the blue region that we had seen in the previous slides. Okay. And similarly, when we are solving this linear program here, then we have all the constraints that we had for the original linear program plus y less than or equal to 1. Okay. So, then the feasible region for this linear program is the orange portion that was shown below in the previous slides. Okay. So, now we can represent this information of the solutions that we obtained so far. The top box here, or we can say the node of this tree here, the top node here has this solution 4 comma 3 by 2, and the objective function value is 23.5. This was obtained by solving the linear relaxation of the original integer program, and then since we had this 1.5 as a fractional value, so therefore we created two branches here. One was for y greater than or equal to 2, the other one was y less than or equal to 1. For this branch, when we solved the linear program here, we got this solution, and for this one we got this solution here. Okay. This left node here is an integer solution. This is giving us a lower bound of 18. Why is it giving us a lower bound of 18? Because we already have a solution which is having integer values, 2 and 2 both are integers. So, since at this point the objective function value is equal to 18, so the optimal value of the original integer program cannot be less than 18, because there is already one solution which is having the value 18 here. Okay. So, in a way now we have obtained the lower bound for this, the objective function value of the integer program, it is 18. We already had an upper bound which was 23.5, that was obtained by solving the original linear programming relaxation. So, now if we focus on this right node here, so this right node is a fraction solution with z greater than 18. Okay. So, this is still worth exploring. So, you can think that since this node is the solution which is written here has been obtained by solving the linear program here. Okay. So, it is possible that if you solve the integer program in this corresponding region, then you can as well get something as close as 18.33, which is still better than the 18 value here. So, this is still worth exploring. Okay. So, let us focus on this node more. So, since we have this solution 3.33 here, and this is not an integer solution, so we will create now two branches here. One is x less than or equal to 3 and the other is x greater than or equal to 4. Okay. So, we will branch further below this node here. One will be x less than or equal to 3, the other will be x greater than or equal to 4. Okay. So, we get the following when we branch on x less than or equal to 3. and x greater than equal to 4. So, these solutions are represented in these boxes here. So, for the sake of clarity, since we have limited space, we have not shown the solutions that were obtained above this node here. Just we have shown what we get after we put these new constraints x greater than equal to 4, x less than or equal to 3. When we put this constraint x greater than equal to 4, then there is no feasible region. Okay. So, it is called infeasible. So, there is no point of looking further here because there is no feasible point here, and this is kind of a notation that we write z equal to minus infinity if it is an infeasible solution, because we are here trying to maximize the objective function value, and therefore, any value will be greater than minus infinity. So, we just write z equal to minus infinity here. And just to remind you again, this x greater than equal to 4 is in addition to the constraints that were already put before. Okay. So, remember that we first had the constraint for the original linear program, and then we had added either y less than or equal to 1 or y greater than or equal to 2, and then in one of these cases we decided to go further down, and then we added these constraints. So, whenever we are branching, we are always keeping the constraints of the linear program that we have got until now. We are just only increasing the number of constraints that we add here. Okay. And when we have this constraint x less than or equal to 3 here, then we get this solution. So, this point here is saying the same thing, that we have the constraint y less than or equal to 1 plus the constraints of the original linear program when we solve the linear program on these branches. Okay. So, these constraints, either if we add x greater than or equal to 4 or if we add x less than or equal to 3, they are just getting added on top of the constraints that we already had here. Okay. So, since this left node here is infeasible, so this can be ignored completely because there is no feasible solution, leave alone thinking of having the optimal solution. The right node here is an integer solution here because x and y both are integers 3 and 1, but since the objective function value z is equal to 17 and that is less than the solution of 2 comma 2 where we had the objective function value of 18. So, therefore, there is no point in pursuing this branch further, because since this is the solution of the linear program in this region, the corresponding objective function value for the integer program cannot exceed this. Okay. So, we do not need to create any further branches here, not required. And note that one more point to mention is that even if the solution that was mentioned here was fractional, but it was still suppose something like 17.3 here, the objective function value z. In that case also we would not have branched further because the corresponding solution of the integer program cannot exceed the optimal value that you get for the linear program, and therefore there is no point of going further when you already have an integer solution that gives us the value of 18 objective function value. Okay. So, now we do not have any more nodes to explore, or we do not have any more regions of this feasible set to explore. So, we are done here. So, we can represent all the solutions that we obtained in this tree here. So, you can see that these rectangles are different boxes and then these arrows are different branches here. So, the best integral solution that we have is x comma y at 2 comma 2 where z is equal to 18. Okay. So, you can see that below every box where we have stopped or the node where we have stopped, we have written some reason for stopping. For example, below this x comma y equal to 2 comma 2, we have written pruned by integrality. So, since this solution was integer form, so this is the optimal solution for the integer program if we solve the problem in this region. Okay. So, that is why we did not explore this further. Similarly, for this node it is written pruned by infeasibility. So, since there is no feasible region here, so there is no point of looking this further. So, we do not go further below this, and here it is written pruned by bound because this z value of 18 that we already have here. Okay. So, there is no point of going further below here, not required. So, we write it pruned by bound here. So, therefore, the optimal solution is this x comma y 2 comma 2 where z is equal to 18. Okay. So, since we note one more thing here, that in this problem we could have also pruned the branch when we had obtained x comma y 3.3 comma 1 with z equal to 18.3 here. The reason behind that is, even though this 18.3 here is greater than 18, we cannot have the objective function value that is having fractions, because if you remember, the objective function originally was having integer constants 4 and 5, okay, and since x and y are also restricted to be integers, the objective function value cannot take fraction values. So, since we cannot get anything greater than 18.3 here as the optimal solution for the integer program, so the best optimal value that you can get here for the corresponding integer program will be 18 only, and since we already have a solution which is having integer values that attains the value z equal to 18, therefore, there is no point of going further down below here. Okay. Now, even if we go further down below as we had done in the previous slides, there is no harm in that, just that we will not be getting anything better. Okay. So, this kind of reasoning only works when the constants in the objective function or the coefficients in the objective function are integers. So, formally this branch and bound algorithm can be defined as follows. So, we have a list of nodes here. So, these list of nodes are different linear programs that we need to solve. So, initially this list L only contains one node, okay, that is the linear programming relaxation of our original problem, and we will represent x star as the best integer solution that we have found so far and its objective function value as z star. Okay. So, for example, we had this solution 2 comma 2 with the objective function value of 18 in the previous example. Initially, we may not have any integer solution known to us. So, in that case, there will be no x star here and we can set z star to be equal to minus infinity if it is a maximization problem, because any objective function value that you get later will only have value greater than minus infinity. And in each step of this branch and bound, we will pick a node, that is, we will solve a linear program, we will remove it from the set L and do something based on the solution that we observe, okay, and we will repeat this until L is empty. So, suppose a node we look at has optimal solution x with the objective function value z, then there can be several cases that can happen. Okay. So, we have solved a linear program here at a particular iteration of branch and bound, and then there can be some possibilities that can happen. Okay. So, we will check them in this particular order here. Suppose the z value that you get by solving this node here or the linear program is less than z star, that is the best integral objective function value that you already know, then we do not do anything. So, if you remember that when we had got the objective function value of 17 in the last example and we already had an integral solution that was giving the objective function value of 18. So, then there is no point of going further below that branch, because we cannot get anything better. So, therefore, we prune that branch because of bound. Suppose if z is greater than z star and x is an integer solution. So, we have found objective function value which is greater than the best we know so far, and we have an integer solution. So, in that case we can update our integer solution here, and then this node will be considered to be pruned by integrality. So, we will not go further, and then we can have another condition that this z is greater than z star, but this solution that we have obtained is a fractional. So, xi is f, a fractional value which is not a integer. Okay. So, then we will branch on this fractional value that we have, the fractional variable, and we will add two more nodes here. One will be having this additional constraint that xi is less than or equal to the floor value of f here. So, for example, there we had this 1.5, see the floor value of 1.5 was 1. So, we had this constraint y less than or equal to 1 there, and similarly we had y greater than or equal to 2 here. So, this is the ceiling function for the f value here. And if we encounter this situation that there is no feasible solution, then we do not do anything. Okay. So, then the node is pruned by infeasibility. Okay. So, we will end this discussion here and we will continue in the next class. Thank you.